Hi everyone. So in this video, we're going to learn about a new type of integral that's called an improper integral. So in order to get into that, I want to start by just kind of reminding you what is the kind of area interpretation of an integral. So recall that when you take an integral from a to b of a function, whatever number you get, that's going to equal the area, where, area could be positive or negative. And specifically, it's the area bounded by your function, the x-axis, by x is equal to a, and by x is equal to b. So to give a quick example of that, here I have the function, so this is f of x is equal to 1 over x squared. If we take the integral from 1 to 2 of 1 over x squared, so what is our antiderivative? It is negative 1 over x, and we can plug in 2, we can plug in 1, and we get negative 1/2 minus negative 1. And so that's going to be equal to let's see, so we have negative 1 plus 1, so that's equal to 1/2, right? And so what does that 1/2 refer to? Well, it's just this area that I'm shading in blue. So one thing that I mentioned, I think that we don't really talk about, but that is going to become important now, is that whenever we're talking about the fundamental theorem of calculus and we're evaluating integrals, we're talking about a and b as finite numbers, meaning that neither of them is infinity. And so what we'll see in this video is that you can actually take an integral where one of your bounds is infinity, or even where both of them are positive and negative infinity. But we basically need some new tools in order to take those types of limits, because FTC only works when a and b are actually finite numbers. So, what am I talking about here when I talk about an infinite limit? It would look something like this. So what is the meaning of, so now let's say that we're looking at the integral from 1 to infinity of this same function, 1 over x squared dx. So what does that actually mean? Well, it refers to the area of now an infinite region. So it is the area of the infinite region bounded by, so most of the same stuff we said above. So it's going to be bounded by f of x, the x-axis, and then there's only going to be one horizontal bound. So the only bound is going to be x is equal to 1, right? Because basically, if our top bound is infinity, that means we're talking about a region that extends on forever and ever. So basically, we're looking at a region that starts at 1, and then that just keeps going and going and going and going and going. So one thing I just want to make really clear, and I'll try to bring this up in different contexts in this class, is that infinity is not a number. So it doesn't make sense to say the top bound is x equals infinity. X can't equal infinity. No, like x has to be a number, right? So you can't say something equals infinity. So it's important that you don't think of this as being a region that is bounded by infinity, because that just doesn't make sense. What this is really saying is that it's a region that extends on forever in the horizontal direction, or to the right specifically. So one thing that is really interesting about this region is that even though the region itself is infinite, right? Because it doesn't have any like right endpoint. It just keeps going on to the right. Its area is actually finite. And so we'll see this doesn't happen in every situation. So we're going to be looking in all throughout this video at integrals where one of the bounds is either infinity or negative infinity. And we'll see that for some of them, you actually still get an infinite area. So you'll have an infinite region with an infinite area. But in some cases like this one, you have an infinite region that actually has a finite area. And I know that's kind of weird and kind of hard to think about. It's almost kind of like paradoxical, but mathematically it is true that, and we'll see how the math kind of pans out in a little bit. It is true that the area of this infinite region is a finite number. Okay, so how can we actually go about evaluating? So how can we evaluate the integral from 1 to infinity of this function, so 1 over x squared? So what we're going to do is that, as I mentioned, FTC2 only works when the bounds are finite numbers. So it would make zero sense to do FTC2 and plug in infinity. I really don't want to see that. That's like one of my little pet peeves. I don't want to see you plugging in infinity. Infinity is not a number. It can't get plugged in. So what we need to do instead is take that top bound and let's call it t. So we're going to kind of think of the top bound as being a finite number. So what we'll do is that we can find the integral, instead of from 1 to infinity, and let me use some color to kind of stand out here, instead of taking the integral from 1 to infinity, we're going to find the integral from 1 to t, where t is just a number. And what are we going to do with that number t? Well, we're going to try bigger and bigger numbers for t, using larger and larger values for t. Let me use my purple. Does that kind of make sense? So we're instead of thinking of it as the integral from 1 to infinity, we can just do the integral from, like, we already did 1 to 2, right? That's what we did up here. We got 1/2. Maybe next we can do 1 to 5, and we could do 1 to 10, we could do 1 to 100, we could do 1 to 1,000. You can keep plugging in bigger and bigger numbers for t, and as long as you're picking a finite number, as long as you're not plugging in infinity, what you're doing is okay, and it can give you a sense of kind of like, where is this thing heading? So as we mentioned, we already found the one that was from 1 to 2, so let me just write that one down since we had it up there. So we found that the integral from 1 to 2 of 1 over x squared dx, we found that that was equal to 1/2. So now let's do the integral from 1 to 5 of 1 over x squared. So in this case, we take again our antiderivative. We have negative 1 over x. We're evaluating it at 5 and at 1. And so we get negative 1/5 minus negative 1. And so that's negative 1/5 plus 1, which is 4 over 5. So we got a larger result, which makes sense, right? 4/5 is bigger than 1/2 because we're looking at the area of a bigger region. Let's do the integral from 1 to 10. So it's going to pan out basically the same, right? We have negative 1 over x. Now we're plugging in 10 and 1. And so we get negative 1/10 minus negative 1. So that's going to be basically 1 minus 1/10, which is 9/10. Again, it's larger than the one that we got before. Let's do one more. And this last one, maybe we don't even need to do FTC because I think you can kind of see the pattern, right? Because of how the antiderivative works out, you're always going to get basically like 1, when we had 10, we got 1/10 less than 1. When we had 5, we got 1/5 less than 1. So if we have 100, we'll get 1/100th less than 1. So you would get 99 over 100. Or even if you did the integral from 1 to 1,000, then you would get, dx 999, or sorry, too many nines, 999 over 1,000. Okay, so what's happening with these numbers if we take these outputs and we compare them? So for the first area, we got a half, then we got 4/5, 9/10, 99 over 100, 999 over 100. So they are getting bigger, right? These are all, like, if you think of, what do these fractions look like? For sure, you can tell that 9/10 is bigger than 1/2, right? But furthermore, what's happening is that these values are approaching, so these areas are approaching 1, right? They're getting bigger, but they're not getting bigger. Like, it's not like we got, 1/2 and then we got 5 and then we got 10 and then we got 32. We got numbers that are getting bigger, but as they're getting bigger, they're also getting closer and closer to 1. And so from this, what we can conclude is that the integral from 1 to infinity of 1 over x squared dx is equal to 1. That area, that finite area of this infinite region, if you were to, find the area going all the way out, as far as you could imagine possibly going, and beyond that, that area would actually be equal to 1. So, what we just did worked, right? We tested numbers and we could just kind of tell from the trend where it was going, but it's kind of a cumbersome method. And, maybe it feels a little like less for sure than you want it to, right? It doesn't feel totally certain because we're just kind of testing numbers. So it turns out that there is a way to actually calculate this more kind of certainly. So how can we find the integral from 1 to infinity of 1 over x squared dx without having to test numbers? And the answer is that we can use limits. So, what we talked about earlier, and really what we were doing here, right, is instead of putting the upper bound as infinity, we're putting the upper bound as different values. And so we can express that as saying the integral from 1 to t of 1 over x squared. And then what should I put in front of this integral that kind of captures this idea of making t bigger and bigger and bigger? Well, really, we're taking the limit as t approaches infinity. Right? So that is how we can evaluate this integral. And we'll write this down like as an official fact a little bit later in this video, but that's basically going to be our method. So we'll see in a little bit, we're going to actually start by evaluating this integral, and then we'll take the limit afterwards. So we're really kind of forced to do it like that because, as we said, you cannot do FTC2 with infinity as one of your bounds. It just doesn't make sense. So what you have to do instead is kind of put in this t as like a stand-in, and then later you take the limit as t approaches infinity. So, as you can probably tell, we're going to be doing limits in this video. So what's going to happen is, in general, we're going to be, evaluating an integral. We're going to end up with some kind of a function that has t in it because that's our bound. And then we're going to have to take the limit as t approaches infinity of, whatever that function is. And so we need to make sure that we know how to take limits as, x or t or whatever your variable is approaches infinity. So I want to start by doing just kind of a quick review of limits at infinity. So this is something that you should have learned in your Calculus 1 class. And the good news is that we're not going to be doing nearly as many kind of different types of examples as you did in Calculus 1. We're not going to be like doing that thing where you go and divide everything by a number. We're not going to be using the squeeze theorem. We're not doing anything like that. We're basically going to be limited to some pretty simple examples of limits at infinity. So what does it mean to take the limit as x approaches infinity of f of x? So if you take the limit as x approaches infinity of a function, basically think of that as a description, or maybe I'll say it this way, describes what happens to the outputs Or if you're looking at the graph, the outputs would be like the y values, right? So the outputs of your function, as x gets larger and larger. So, at the end of the day, when you're talking about a limit at infinity, that's really what you're talking about, is what's happening to your function as x gets larger and larger. And then if you're taking the limit as x approaches negative infinity of your function, well, that's basically the same thing, but now you're talking about x getting smaller and smaller. What happens to the outputs of f of x as x gets smaller and smaller? So there's a variety of ways to actually evaluate infinite limits. As I mentioned, we're not really going to be kind of delving into those algebraic methods or anything like that. Most of the functions that you need to be able to know what their limit at infinity is are going to be pretty simple functions where if you're familiar with what their graph looks like, that will be enough to tell you what the limit is. So we're going to go through some of those most important ones. These are going to be the ones that basically I would expect you to be familiar enough with the shape of the graph that you would be able to tell me what the limit of the function was at positive or negative infinity without having to do any extra work really. So these are, there might be some other examples that come up, but these are basically the most important ones. So the first graph I have here is f of x is equal to e to the x. So f of x is equal to e to the x has a horizontal asymptote to the left, and then to the right it gets bigger and bigger and bigger. So the limit as x approaches negative infinity of e to the x is going to equal 0, right? Because as you plug in smaller and smaller values for x, the function gets closer and closer to the x-axis, kind of getting closer to a height of 0. On the other hand, if you look at the limit as x approaches positive infinity of e to the x, well, now the graph is going up and up and up and up, right? So the limit as x approaches infinity of e to the x is infinity. Okay, so next graph is f of x is equal to ln of x. So just a quick tip for being able to remember what the graph of ln of x looks like. It's just the inverse function of e to the x. So I think it's really important. I think at this point, if you're in Calc 2, you really should know what the graph of e to the x looks like. And then if you know what that looks like, just kind of roughly the shape, well, ln of x is the inverse. So all of the x and y coordinates flip. So for example, there's a point here, there's a point at e, which is like 2.7, and then 1, and it would have a vertical asymptote instead of a horizontal asymptote. So it looks like that. So that's the same as the graph that's down here. I just wanted to show you on this upper graph so you could kind of compare them. So here's ln of x. It doesn't make sense to take the limit as x approaches negative infinity because there is no graph past 0. So we're just going to take the limit as x approaches positive infinity, and that would be infinity. So even though the graph isn't kind of going up in this really, like if you look at e to the x, it's like getting steeper and steeper, right? It's really kind of shooting straight up. This one is kind of creeping up slowly, but it does go up. So as you plug in bigger x values, you do get bigger y values. It just does so kind of more slowly than other functions. Okay, so this one is f of x is equal to 1 over x cubed, but I just kind of picked that as a stand-in for a general type of function. So if you have any function that is of the form 1 over x to the n, so the limit as x approaches negative infinity for really any real number n, this is going to be any positive number n. So, what we're about to write goes for 1 over x to the 1/2. It goes for 1 over x to the 4th. It goes for 1 over x to the 5th. Any number you want to pick for n. The limit as x approaches negative infinity is always going to be 0. And the limit as x approaches positive infinity is also going to be 0. And it's basically because their graphs will always look more or less like this one. Depending on what number you have as your exponent, the overall shape will be a little different, but they'll always have these horizontal asymptotes where they'll settle down towards the x-axis. All right, so next one I think is probably the least familiar out of any of these graphs. So this one is f of x is equal to inverse tangent of x, which, you know, it might not have stood out to you as being an important function in earlier classes, but we've seen that it actually comes up a lot with integration just because it's, you know, the derivative of inverse tangent of x is like a pretty nice function. So we end up integrating it pretty commonly. So again, similarly with the graph of ln of x, the way that I would try to remember what the graph of inverse tangent of x looks like is, you know, if you think about the graph of tangent, so tangent basically has this kind of a shape, and then it has vertical asymptotes at negative pi over 2 and pi over 2, and then it repeats itself over and over. And so if you have the inverse function, it's no longer going to have vertical asymptotes, it's going to have horizontal asymptotes. And so because this graph has horizontal asymptotes at negative pi over 2 and positive pi over 2, that tells us that the limit as x approaches negative infinity of inverse tangent of x is equal to negative pi over 2. And the limit as x approaches positive infinity of inverse tangent of x is equal to positive pi over 2. Okay, last example, this one's kind of a odd one out. So this is the graph of sine of x. So this function is really different from the other ones, right? Because it doesn't, you know, if we look at some of these earlier graphs, so if you look at like e to the x, that one goes up and up and up, right, to the right. Whereas if we look at like 1 over x cubed, that one flattens out. Or inverse tangent, that one flattens out. This graph doesn't shoot way up, it doesn't shoot way down, it doesn't flatten out, it just kind of repeats itself over and over. And so in this case, you would actually say that the limit as x approaches negative infinity does not exist. And same thing with the limit as x approaches positive infinity also does not exist. So let me just kind of label this in case people are looking at the lecture notes. So these basically are limits you should know. Like these are basically going to be the building blocks of the problems that we work on later in this video. So there's one more thing that I want to bring up before we get back to how this is actually used with integration, and that's what's called L'Hopital's rule. So this isn't going to come up a lot, but it might come up here and there, and I just want to remind you of how it works. So L'Hopital's rule says that if you have, basically it's used when you're taking a limit of a fraction, you know, one function over another. And so if the limit as x approaches a, and so here a could be positive or negative infinity, or it could be a number, just any kind of limit. So if x approaches, the limit as x approaches a of the numerator is equal to positive or negative infinity, and the limit as x approaches a of the denominator, which I'll call g of x, is also equal to plus or minus infinity, or the limit as x approaches a of the numerator is equal to 0, and the limit as x approaches a of g of x is equal to 0. So basically you can only apply L'Hopital's rule if both the numerator and denominator are going to positive or negative infinity, or if both the numerator and denominator are going to 0. And so if you're in either of those cases, then it's going to be true that the limit as x approaches a of f of x over g of x is the same thing as taking the limit as x approaches a of the derivative of f of x over the derivative of g of x. And notice here, you're not using the quotient rule, you're literally just taking the derivative of the numerator, derivative of the denominator. Okay, so let's now get back to how this is actually used. So we just saw a few minutes ago that the integral from 1 to infinity of 1 over x squared, we saw that it was 1. And we saw that because we used, we plugged in different numbers. So now let's actually do it with limits. So we're going to find the integral from 1 to infinity of 1 over x squared. So let's apply that rule that we wrote down earlier, which is that we're going to be now taking the limit as t approaches infinity of the integral from 1 to t. So we're basically kind of subbing out that infinity symbol for a t, and then we're going to later take the limit as t approaches infinity. So again, I've said this before, but I'm just going to say it one more time. It's really important that you focus first, like you can almost cover up the limit, forget about the limit, focus on evaluating the integral, and then take the limit at the end. So I'm just going to kind of keep writing the limit down as we focus on the integral part. So we're going to have the limit as t approaches infinity. So let's focus now on the integral. So what would the antiderivative of 1 over x squared be? Well, we already saw it's negative 1 over x. And then we have to evaluate that at t and at 1. And I know we're not used to plugging in another letter, but it works exactly the same as plugging in a number. So again, we're still taking the limit as t approaches infinity. So we'll just write that down and we'll do that later. And now we want to actually plug in t. So we're going to get negative 1 over t minus negative 1. And so that's going to give us the limit as t approaches infinity of negative 1 over t plus 1. So this part, or actually maybe I'll say as this part, this fits with one of the limits we talked about on the previous page, right? We talked about that if you have 1 over x to any power, and that includes 1 as that number n, 1 over x to any power, the limit is always going to be 0. And so that means that this part, the limit is 0. And so what is the answer for this overall limit? Well, we get 0 plus 1, which is equal to 1. So that agrees with what we found earlier by plugging in numbers. So there's a word that I'll write down again as like a more official definition pretty soon. But when you get an actual answer for your integral, which we'll see doesn't always happen, there will be some times when you have an integral with an infinite bound where you'll actually find that the area is also infinite. That can happen. So when you have a finite number as your answer, then this is what's called converging. So you would say that your integral converges. Okay, so I want to do another example that is like very similar. Maybe I'll use a different color. Let's do magenta. So what if we just change it to 1 over x, which is like, very, very similar function to 1 over x squared. So let's see what happens if we do that. So again, how do we actually evaluate this? Well, we can't leave infinity as our upper bound. We have to rewrite this as the integral from 1 to t and then take the limit after the fact. Okay, so what is our antiderivative in this case? Well, the antiderivative of 1 over x is ln of absolute value of x. And then we're evaluating that at t and at 1. But one thing I want to point out is that if we're doing an integral from 1 to infinity, well, that means that t is always going to be a positive number, right? So we actually don't really need the absolute value sign, because it would be different if we were taking a limit as x approached negative infinity or as t approached negative infinity. But because t is approaching positive infinity and the lower bound is also positive, you're only going to be plugging in positive numbers. Okay, so what is our, we still have our limit. And now we're going to have ln of t minus ln of 1. So ln of 1 is equal to 0, actually, right? Because ln is asking what power you have to raise e to get whatever number. So what power do you have to raise e to get 1? The answer is 0. So we have the limit as t approaches infinity of ln of t minus 0. So we can just focus on ln of t. Oops. So this is another one that we saw on the previous page, right? We saw that when you have, we called it ln of x, but it doesn't really matter. We saw that if you take the limit as x approaches infinity of ln of x, you get infinity. And so therefore, our answer here is actually infinity. So one thing that's a little bit different in this class compared to in Calculus 1 is that we're not going to say that the value of this integral is infinity. We're just going to say that it diverges. So as soon as you get positive or negative infinity as your answer, you don't need to specify which one it is. You just say, oh, it diverges. It basically means that there is no, finite number representing the area. And so it doesn't matter if it's positive or negative infinity, just say it diverges. So I just want to quickly show you what, we saw earlier that if you take 1 over x squared, the area was 1, whereas when you do 1 over x, suddenly the area is not a finite number. And you can kind of see why that is. So the graph in blue is 1 over x squared, and notice that 1 over x squared gets closer to the x-axis faster. Whereas 1 over x, it still flattens out, but it takes considerably more time. You can definitely notice the difference between the two. And I know it probably is a little hard to wrap your head around, but it just so happens that the graph in blue, 1 over x squared, it gets closer to the x-axis faster enough so that it is able to have a finite area, whereas 1 over x, even though it looks like it should, it doesn't have a finite area. So very, very small differences in the functions can lead to a totally different result. Okay, so I now want to write down just some general definitions just so that we have these real definitions written down, and then we'll spend the rest of the time doing examples. So we'll see in the next video that there are actually other types of improper integrals. So the first part is called an improper integral of a type 1, and that's the type that we've been looking at so far in this video, where one of the bounds is infinity or negative infinity. And so we'll see in the next video that there is another kind of different type of integral that's also called improper, but we'll get to that in the next video. Okay, so first of all, so this first statement I'm going to write down is kind of a technicality. I wouldn't worry too much about it, but I just kind of have to write it down as part of the definition. So if the integral from a to t of f of x dx exists for all t greater than or equal to a, then, so this next part is the important part. So the integral from a to infinity of f of x dx is equal to, as we saw, the limit as t approaches infinity of the integral from a to t of f of x dx. So again, the idea is basically just to kind of forget about the infinity part temporarily so that you can focus on the integral and evaluate that, and then take the limit at the end. And this first part, just don't worry too much about it. It's basically, you won't need to worry about this until the next video, but yeah, basically all the examples we'll see in this video, that first statement will be true for. It's just, you might run into an issue if your function has some kind of a discontinuity, but like I said, we'll get to that next time. Sorry, this was kind of bothering me. Okay, so next one, and we'll see an example of this type in a little bit. So if instead you're trying to take the limit, or one of your bounds is negative infinity, then it's going to have to be true that this integral exists for all t less than or equal to b. But again, here's the important part. So the important part is that the integral from negative infinity to b of your function is going to be equal to the limit as t approaches negative infinity of the integral from t to b of f of x dx. And I forgot the dx for some reason. Let me fix that. So it's basically the same thing that we wrote above. It's just that if now your lower bound is infinity, well, then that means that you should be taking the limit as t approaches negative infinity, and t should be the lower bound instead of the upper bound. So it just kind of, makes sense, but is very similar to what we did earlier. So one more thing I want to write down that we just talked about is that if basically one of these limits, so if the limit exists, then the improper integral is convergent, or you say it converges. If the limit does not exist, and so when I say does not exist, basically that could happen in a few different ways. One is that something like, remember when we talked about a few minutes ago, the graph of sine of x, how that limit doesn't exist. So something like that could happen, and we'll see an example like that. But typically, this happens when the limit is either equal to plus or minus infinity. So basically when you do your limit, if you get positive or negative infinity as your answer, you just say that the integral diverges. Okay, so let's do a few examples. So we already did 1 over x squared, we did 1 over x. Now let's do one that is of the other kind of type. So we're going to put negative infinity at the bottom and 0 at the top. So we're trying to find the integral from negative infinity to 0 of x times e to the x dx. So first step is to rewrite it as a limit. So it's going to be the limit as t approaches negative infinity of the integral from t to 0 of x e to the x dx. So what do we have to do in order to evaluate this limit? Well, we actually have to use integration by parts, right? Because it's x times e to the x. So let's kind of focus now, maybe let's even just forget about the limit for a second and just focus on this integral, and then we'll kind of come back to putting the limit back. So to do this, I'll just rewrite it down here. So we have the integral from t to 0 of x times e to the x dx. We want to use integration by parts. So for this integration by parts, we would be letting u equal x, du would be equal to 1 dx, dv would be equal to e to the x, and v would be equal to e to the x. Oops, sorry, I forgot a dx. So I know I'm going through this kind of quickly, but it's because we've done this example actually in an earlier video. And so what would this integral come out to be? Well, it would be u times v. So that would be x e to the x, and we have to evaluate that at 0 and at t, minus the integral of v du. So that's going to be e to the x times 1 dx, which is just e to the x dx. Okay, so let's start plugging in t, and then we can simplify this other part. So we ended up with, if we plug in 0, we get 0, right? If you plug 0 into x times e to the x, you get 0 times 1, which is 0. But then from that, we need to subtract plugging in t, so that's t times e to the t. And then what's the antiderivative of e to the x? It's e to the x. And we have to evaluate that again at 0 and at t. And so that's going to give us negative t e to the t minus, so first thing we do is we plug in 0, so that's e to the 0, which is 1. And then this one, next one is going to be minus a negative, right? Because in FTC2, we subtract, but we also have a negative sign here. So it's going to end up being plus e to the t. Okay, so what does this all come out to be altogether? Well, we get negative t e to the t minus 1 plus e to the t. Okay, so now that we know what our integral is, now we can go and put that back in and take the limit. So we're going to take the limit as t approaches negative infinity of this whole thing. So negative t e to the t minus 1 plus e to the t. So with limits, sometimes it's nice you can split them up with addition, kind of like when you're taking a derivative or an integral. So we can focus on each of these kind of individually. So let's do that. So let's take the limit as t approaches negative infinity of, we'll start with just negative t e to the t, and then we'll do the limit as t approaches negative infinity, of negative 1, and then to that we'll add the limit as t approaches negative infinity of e to the t. So let's actually leave behind this first part for a moment. We'll come back to this, and let's just focus on these other two. So what is the limit as, I'll circle that, so remember that we come back to it. What's the limit as t approaches negative infinity of negative 1? Well, negative 1 is just a constant number, so it's just negative 1. Negative 1 is always negative 1. Doesn't matter what you're plugging in for t. And then what about the limit as t approaches negative infinity of e to the t? Well, we talked about that one earlier, right? That was this one. E to the limit as x approaches negative infinity of e to the x is 0. So this one is going to be, oops, that's the wrong page. So it's going to be negative 1 plus 0. And then how do we deal with this first part? So this first part, we actually have to use L'Hopital's rule. And I know it might not look like a L'Hopital's rule issue, but we do have to use L'Hopital's rule. And the reason for that is that we have a product where we're multiplying together infinity and 0, right? Like if you were to try to take the limit as t approached negative infinity of negative t, you would get infinity. And then if you try to take the limit as t approaches negative infinity of e to the t, you would get 0. And so negative infinity, or infinity times 0, is another type of indeterminate limit. And so basically we want to rewrite this as a quotient so that we can apply L'Hopital's rule. So let's rewrite this as the limit as t approaches negative infinity of negative, so we can rewrite it as t over e to the negative t. Right, because that's exactly the same as what we had there. If you put negative t as an exponent in the denominator, that's the same as having positive t in the numerator. And now this is actually of the form infinity over infinity, right? Because the limit as t approaches negative infinity of t is negative infinity, and the limit as t approaches negative infinity of e to the negative t, well, that's the same as taking the limit as t approaches positive infinity of e to the positive t. And so it's going to be infinity over infinity. So we can take the derivative of each. And let's just maybe put that negative sign on one of them so that we can include it in the derivative. So we take the derivative of the numerator, we take the derivative of the denominator, and we end up with negative 1 over negative e to the negative t. And so now we're actually good. So now we have the limit as t approaches negative infinity of 1 over e to the negative t. So now if we plug in big numbers, right, or sorry, negative small numbers, well, we also have a negative sign in the exponent. So they kind of counteract each other. And so this is now of the form 1 over infinity. And so that limit is going to be 0. And so what's our answer? Well, we now have negative 1, or we have 0 minus 1 plus 0. And so altogether that gives us negative 1. So just to recap again, we just basically, if you have something that is a product where one of the things you're multiplying is 0 and the other one is infinity, then there's always going to be a way for you to rewrite it as a quotient where one of the things goes to infinity or 0. Like it's either going to be 0 over 0 or infinity over infinity. And once you have it in that quotient form, then you can use L'Hopital's rule. All right, one more type of example I want to look at. So this is something we haven't talked about yet, and I kind of have to add it to my list. But let me first write down the problem, and then we'll kind of write down, we'll go back to that like general rules page and add some stuff there. So now what if we're taking the integral instead of from, a number to infinity or infinity to a number, what if our upper and lower bounds are both infinite? So the integral from negative infinity to infinity of 1 over 1 plus x squared. So how can we do this? We basically just want to split it apart into two integrals. So we're going to rewrite this as the integral from negative infinity to, and we can pick whatever number we want to split it up. So we might as well pick an easy number like, let's say, 0. So we can rewrite this as the sum of the integral from negative infinity to 0, and then the integral from 0 to infinity of 1 over 1 plus x squared. Right? So it's just like an integration rule that we learned at the beginning of the class. And so now we can treat each of these individually. So the first one is going to be the limit as t approaches negative infinity of the integral from t to 0 of 1 over 1 plus x squared dx, plus the limit as t approaches positive infinity of the integral from 0 to t of 1 over 1 plus x squared. So what do we get for these antiderivatives? Well, it's just inverse tangent, right? So we're going to have the limit as t approaches negative infinity of the integral from, we take the antiderivative, which is inverse tangent, and we're evaluating it at 0 and at t. And then here we're doing the limit, and then we're taking, again, the same antiderivative and evaluating it at 0 and at positive t. Okay, so what do we get when we plug in these things? Well, inverse tangent of 0 is just 0. So we're going to have the limit as t approaches negative infinity of, so 0 would give us 0, and so we're just left with negative inverse tangent of t. Negative because it was the second part of FTC because we were subtracting. And then here we have the limit as t approaches infinity of, now the t is positive, right? Because that's the first thing. So now we have inverse tangent of t as a positive, and then subtracting 0, but 0, inverse tangent of 0 is just 0. Okay, so let's go back to our inverse tangent. So when you have inverse tangent, the limit as you approach negative infinity is negative pi over 2, and the limit as you approach positive infinity is positive pi over 2. So let's go and put those in. So for the negative infinity part, we ended up with negative pi over 2 plus, and then here we have positive pi over 2. And so together that's going to be pi over 2 plus pi over 2, which is pi. So we just split it up into two, and kind of then from there, it's just like the other one. So I just want to add this to our kind of list of facts. And then I want to do one more example just to kind of show how in certain situations, when you have an integral that goes from negative infinity to positive infinity, we'll see when we get there. So let me just write down this other fact, which is that if both the integral from, let's say, how do I want to say this? The integral from negative infinity to a of f of x dx, and the integral from a to infinity of f of x dx, if those are both, if both these converge, so if they're both convergent, then you can say that the integral from negative infinity to positive infinity of f of x dx is the sum of these two integrals. For any, and you can pick a to be any number you want. You know, usually you probably want to pick like an easy number like 0. So one thing I want to point out here that's really important is that in order for you to even use this method of taking this limit and splitting it into two pieces and adding them up, it needs to be true that both halves that you're breaking it up into, both of those have to converge. So for example, let's say that you split up your limit and you got, negative infinity when you evaluated the first one, and you got positive infinity when you evaluated the second one. It would not be valid to add those up and say, oh, okay, negative infinity plus infinity equals 0. So infinity doesn't work that way. It's not a number. So you can't just say negative infinity plus infinity equals 0. It just doesn't work that way. And basically this whole idea of splitting up this integral into two pieces and adding them together, it relies upon the fact that each piece separately converges. So what this means for you is that if you take your integral and you split it into two pieces and you start evaluating the first one, if the first one diverges, you don't even have to bother with the second one. As soon as one of the two pieces diverges, the whole thing diverges. So it's actually kind of a time saver. If you evaluate the first one and you get a finite number, well, then you have to still evaluate the second one. But if you evaluate the first one and you get positive or negative infinity, well, then you're done. You don't need to do anything else. You can just say the whole thing diverges. Okay, I want to look at one more example that's a little bit different from some of the other ones. So let's say that you're trying to evaluate the integral from 0 to infinity of cosine of x. So we have to rewrite this, right, as the limit as t approaches infinity of the integral from 0 to t, integral from 0 to t of cosine of x dx. So we still have our limit. And then we take our antiderivative. Antiderivative of cosine is sine. So we have sine of x, and we're evaluating that at t and at 0. No, that's right. So now we want to plug in our bounds. So we have the limit as t approaches infinity of, so sine of t minus sine of 0. And sine of 0 is just 0. So really all we're trying to do here is find the limit as t approaches infinity of sine of t. And so this is one we actually talked about earlier, right? So what's the deal with sine? Well, if we look at the graph, it goes up and down, right? It vacillates, right? It doesn't settle into one value. It doesn't, increase without bounds upward. It doesn't decrease without bounds downwards. It just kind of goes back and forth. And so the limit does not exist. And so this would be an example of an improper integral that diverges not because your answer is positive or negative infinity, but because the limit just doesn't exist for kind of a different reason. So in this case, you would just say, okay, it diverges. So why does this make sense in terms of, areas? Well, if we look at the graph of cosine of x, so here I have the graph of cosine of x pulled up. If you think about, taking the area from 0 to a particular x value. So, for example, you go 0 to pi over 2, or maybe you go 0 to pi or 0 to 3 pi over 2. because the graph lies both above and below the x-axis, it's going to kind of switch off whether you're getting a positive area or a negative area, right? So like if you go from 0 to pi, the areas will cancel out and you'll have an area, a total value of 0. But then if you go a little bit further, it will become negative, and then you go further and it'll become positive. And basically because these positive and negative areas will keep canceling each other out, it doesn't matter how far out you go for your x values, the bigger and bigger x gets, it's still going to be, the area is still going to be kind of canceling each other out back and forth over and over. And so that's why, the area is not necessarily infinite, but it still diverges because it doesn't settle in on one specific area. So most of the cases we're going to see in this class are going to be improper integrals that diverge because you get an infinite value or negative infinity, but there are cases like this as well where it diverges for a different reason. All right, that's it for this video. I'll see you all in the next one.